Good day, students. This clip we're going to be going over number 16 to 20. This is part 4 of the AP Calculus multiple choice release questions for 1969. So let's go ahead and take a look at question number 16. So uh, it says if y is a function of x such that y, the first derivative of y prime is greater than 0 for all x, and the second derivative is less than 0 for all x, which of the following could be part of the graph of y equals f of x? Okay, so these two conditions hold for the entire domain of y. Okay, the first derivative is greater than 0, positive, and the second derivative is less than 0, negative. Okay? Okay, so in this problem, we're going to be using the first and second derivative tests in collaboration with each other, and then we should be able to use that to identify which of these graphs fits the criteria. Okay? So for the first derivative, when y prime is greater than 0 or positive, what does that mean? It basically means that the graph of the function y is going to be increasing on that interval. It's going to be increasing. So we have a situation where the graph is going upwards from left to right. Okay? It could be curving upwards or it could be concave up or concave down. So we don't know what the concavity is, but we guarantee that for the entire domain, the function should be going upwards. It should be increasing. So using this test, we can basically eliminate some candidates from here. All right, so which of these functions is not increasing in the entire domain? Let's see. Option A is increasing, this is good. Option B is increasing in the entire domain, which is good. Option C is decreasing, eliminate that. Option D was increasing before, but at a certain point it starts to decrease. So the derivative is not positive. The first derivative is not positive in the entire domain. It was positive up to this point, and then here it becomes negative. Okay, it was positive in this area, and then it switched to negative here. But the criteria is that it must be positive for the entire domain. So scratch that out. And this one is increasing on the entire domain, so it's good. So we have three choices now. Now, if we look at the second derivative, then we'll be able to identify what the correct choice is, all right? So the second derivative is less than 0. So what does that tell us? This tells us about the concavity, okay? If the second derivative is less than 0, it's concave down. If it's greater than 0, then it's concave up, okay? So here it's less than 0, so it's concave down. That means that it's going to be curving facing downward as it increases, okay? If it has any portion where the graph is caving upwards, then you know that that's not a candidate for consideration. So let's look at the options we have. This graph option A is concave up for the entire domain. So basically the second derivative, this is concave up, the second derivative in this function is um, greater than 0, okay, or negative. But we want it, I'm sorry, or positive. We want it to be less than 0 or negative, so this is not a good answer, okay? If you look at option B, you can see that it's concave down for the entire domain as represented here. The second derivative is less than 0. This is what concave down means, it's facing downward, so this is exactly what we want, all right? How about option E though? You notice that at a certain point from here to here in this interval is concave up, right? And then for this interval from here to here, it's concave down. But we want it to be concave down on the entire domain. So this area kind of messed this stuff up because here the second derivative was greater than 0, which is no good. But here it was less than 0, which is what we wanted. So since this one is not, since the second derivative is not less than 0 for the entire domain in option E, it does not meet the criteria. So the answer is B. Increasing, concave down. Okay? All right, so this is concave down, and y prime greater than 0 means that the graph is increasing. Increasing, concave down, combine these together, you have a graph looking like this, all right? So there you have it. Okay, let's take a look at question 17. All right, so for question 17, it says the graph of y equals 5x to the fourth minus x to the fifth has a point of inflection at. So when do you have a point of inflection? You have a point of inflection when the second derivative changes from positive to negative or from negative to positive. Okay? So the point where the second derivative changes sign is basically where you have a point of inflection. If you have positive to negative, you are having a concave up switching to concave down. Okay, it was concave up before, and then it switched to concave down. You have a switch in concavity. So the point where that switch happens, that's your point of inflection. If the second derivative changes from negative to positive, where it was negative before, it was concave down, and then when it switches to positive, it became concave up. So here we have a point of inflection where the sign change happens. Okay. All right, so you just have to keep this in mind. It's not when, a point of inflection is not when the second derivative equals zero. This is misleading. Don't do that. Equals zero is necessary, but it's not sufficient to conclude that we have a point of inflection. All right. This helps you find out the areas where you have to check for sign change, because in order for something to switch from positive to negative, it must be zero first, or if one goes from negative to positive, it must be zero first before it switches sign. Okay. All right. So what we're going to do is we're going to create some test candidates, some candidates to create our intervals, pick some test points, and then see what happens before and after each boundary point. All right. So to find the points that create our regions, we need to find what the second derivative is, set it equal to 0, and then we're going to do the second derivative test, all right? Okay, so y equals 5x to the 5th, 5x to the 4th minus x to the 5th. We're looking at the second derivative here, not the first, so differentiate it first. Y prime equals, using the power rule, we have 4 times 5 times x to the 4 minus 1 using the power rule, minus 5 times x to the 5 minus 1 using the power rule again. Okay? All right, so the first derivative, y prime, is going to be 20x to the third minus 5x to the fourth. All right, so the first derivative tells us whether it's increasing or decreasing. That's not what we want, so let's differentiate it again. Y double prime, second derivative using the power rule. Again, we'll have 3 times 20, x to the 3 minus 1, minus 4 times 5, x to the 4 minus 1. Okay, so the second derivative is going to be 60x squared minus 20x to the third. Okay, all right, so to get the boundary points, we're going to set y double prime to 0 and solve. So we're going to have 60x squared minus 20x to the third equals 0. We can divide everything by 20. So we have 3x squared minus x to the third equals 0. Okay. All right. Let's factor this. Factoring out x squared. X squared times 3 minus x equals 0. Okay. So boundary points are using the zero product property are when x squared equals 0 and 3 minus x equals 0. If you solve this, you have x equals 0. And for this, x equals 3. Okay? All right, so these are points of inflection? Absolutely not. These are the boundary points that we're going to use to test to see where the sign change. If a sign change happens at these 2 points. They're just candidates, right? But we don't know yet. Okay? So to see which, if any are points of inflection, we're going to create a boundary. And let's graph it. We have 0 and 3. Okay, so this is region 1, region 2, region 3. Okay, now what are we going to test here? We're looking for a sign change for the second derivative, right? All right, so anything less than 1, let's use -1 for this region. Let's use 1 for here, and then let's use 4 for here. Okay? Okay, so we're looking for the change in y double prime. So y double prime equals, I like to use a factored form, x squared times 3 minus x. Remember, all we just care about is the sign, okay? All right, so when we differentiate for interval 1, we're testing x equals -1. So what's the sign of the second derivative in interval 1? That's the question, okay? So second derivative is basically -1 squared times 3 minus negative 1. Okay? So what do we have? Negative 1 squared. If I square this, it's going to be a positive times 3 minus minus 1 is going to be 4, which is positive. Positive times positive is positive. Notice I don't care about the numbers. Like, all I just care about is the sign. Is it positive or negative? So after working this out, it's positive. Okay, in order for 0 to be a point of inflection, the sign in region 2 must be negative, or else 0 is not a point of inflection. Okay? Alright, so let's go ahead and test the second interval. The test candidate was x equals 1. So what is the sign of the second derivative in this interval? Positive or negative? Well, let's work it out. So we're going to have plug this into the second derivative. 1 squared times 3 minus 1. Okay? 1 squared is going to give us a positive result, which is 1. And then 3 minus 1 will give us a positive result, which is 2. Positive times positive is positive. So guess what? We do not have a change in concavity. It's positive here. So in this interval, the second derivative was positive, which indicated that the concavity is upwards, concave up here. And then the second interval, the second derivative is positive, which also indicates that the graph is concave up. So there wasn't any switch in concavity here. Hence, 0 is not an inflection point. All right. In order for 3 to be an inflection point, this region has to be negative. All right. The second derivative has to be negative here, or else we have no inflection points on the curve. All right. So what we're testing here is for region 3. Our test candidate was x equals 4. Remember, all I care about is the sign. So y double prime is going to be 4 squared times 3 minus 4. That's what you get when you plug in 4 into the second derivative. 4 squared is 16, which is a positive number, times 3 minus 4 is negative 1, which is a negative number. Positive times negative is negative. So in interval 3, the sign of the second derivative actually changes. It's not concave down. So whenever you have a switch in the sign or concavity, switching the sign of the second derivative or the concavity, the point where the sign change happens is a point of inflection. Okay? So this is the only point of inflection that we have here. Okay? So if we want to find what the actual value of the point is, we know the function is y equals 5x to the fourth minus x to the fifth. So all we'll just do is plug in 3 here and then work it out. Well, it's not really necessary. Let's go and look at the question. We can clearly see that the option is B because the x coordinate is 3. Okay? All the other ones are wrong. If you wanted to get 162, you just simply plug in 3 into this function and then you work it out and get 162. So basically you evaluate y at x equals 3 and you have 5 times 3 to the fourth minus 3 to the fifth power, and then that should give you 162. Okay? Alright, so there you go. The answer is option B. Alright, let's move on to the next question, question 18. It says if f of x equals 2 plus absolute value of x minus 3 for all x, then the value of the derivative of f prime at x equals 3 is. Now, if you know what the nature of this curve is, you should be able to do this without doing any work. Okay? So, when does the derivative fail to exist? There are 4 cases where the derivative fails to exist. So, f prime of x is non-existent when you have, 1, a vertical tangent, or if you have a corner, or if you have a cusp, or if you have, number 4, no tangent. Okay, like if you have a discontinuity of some sort. All right, if you look at the absolute value, this is a typical example of a corner. So if you have an absolute value function, you have a corner situation here. So option 2 applies here. So we have to be careful. Where does the corner happen in this function, f of x equals 2 plus the absolute value of x minus 3? The value inside the absolute value bars, if you set that equal to 0, that's where you have the corner. Okay? So let's see, where is that? If I set that equal, extract that, x minus 3 equals 0. If I solve that, x equals 3, we have a corner. Okay, sharp corner. All right, the left and right hand derivatives are going to be different because you have a v. If you remember what your absolute value function looks like, you have a that point where the vertex of that v resides. That's where you have the corner. Okay, so you have a sharp corner here. The left and the right hand derivatives are different, hence the derivative at this point is non-existent. Okay, so since we have a corner at x equals 3, the derivative at x equals 3 is non-existent. So that's where you have it. That's how you have it. Okay. All right. So to the left of the corner, you just this function becomes it's like this is like a piecewise defined function. So like let's say to the left of the corner you have 2 minus x parenthesis x minus 3. All right. That's for x less than 3. And then to the right of the corner you have 2 plus x minus 3. And you see how the derivatives are different. Okay, but on that point where the corner is, the derivative is non-existent because on the left and the right you have different derivatives. Okay. All right, so there you have it. Okay, let's move on to question 19. It says a point moves on the x-axis in such a way that its velocity at time t is given by v equals the natural logarithm of t over t. At what value does t attain its maximum? So this is another example of optimization, or extrema to be more specific. Looking for the maximum or extrema here. So you basically know that the extrema happens at the critical points where the derivative changes from positive to negative or negative to positive. In a maximum situation, we need the derivative to change from going up to going down. Okay, and you know if a function is increasing, you know that the derivative is going to be positive, and when it's decreasing, it's going to be negative, all right? So what we'll do is look for the critical points here in this graph for t greater than 0, and then look for where the sign of the first derivative changes from positive to negative on any of those critical points, and that will be our maximum. Okay, as you can see here, we have at least one or not, all right? So velocity function is the natural logarithm of t over t. We're going to look for the first derivative, basically the acceleration. So dv dt is going to be, we're going to use the quotient root here. So let me call the numerator u, okay? And then call the denominator v. So what is u over v prime? Let's do a real quick review on our quotient rule. U over v prime is equal to v u prime minus uv prime over v prime, right? V squared, sorry. So you have low d high minus high d low over low squared, all right? So there you have it. So that's what I'm going to do here. Let me break it down. I know some of you are really smart. You can do this mentally, but I'm going to break it down so that you don't get confused, okay? So what I'm going to do is I'm going to go t times ln t prime, right? So that's low d high minus uh, ln t, that's u, v prime, t prime, that's high d low, and then over low square, t square. Okay, so that's what I'm doing here. All right, so remember your formula for the differentiation of logarithmic functions, right? Let's put it on the side. Uh, d dx of the natural logarithm of x is 1 over x. Okay, so you need to know that. So let's go ahead and apply that here. So we're going to have t times the derivative of ln t is 1 over t minus ln t, the derivative of using the power rule to find the derivative of t is just 1 times 1 over t squared. Okay? All right, now let's simplify that. So we're going to have, what are we going to have? The t's divide out. Let's divide out. And we're going to have 1 minus the natural logarithm of t over t squared. Okay? All right, so we're looking for the critical values. So to do that, we have to set this derivative equal to 0. multiply both sides by t squared. Remember, t is bigger than 1, so we're going to have 1 minus the natural logarithm of t equals 0. To get t by itself, add 1 to both sides. Actually, let's add ln t to both sides. So we have ln t equals 1. And then to isolate t, we use the inverse of the natural logarithmic function, which is e. So e to the ln t is equal to e to the 1. These two cancel out, so you have t equals e to the 1, or just e. Okay? So is this a maximum or a minimum? Well, we don't know. It's just a critical point. We have to test it, right? There must be a sign change on this value right here in order for it to qualify as an extreme, a max, or min, okay? All right, in this case, it must be a change from the positive to the negative for it to be a maximum, or else it's a minimum. If a sign change happens. Okay, so this is E. So we know what E is approximately 1.7 actually, sorry, it's 2. Anyway, E is approximately, I forgot, E is approximately 2.717 and goes on and on and on. 2.717. Okay, so yeah, let's pick a value that's less than that. This is approximately 2.7, and a value greater than that. We can't pick anything less than anything 0 or less, right? Because it has to be bigger than 0. All right, so what can we pick to the left of this interval? We can pick, let's put the 0 here, and this goes here forever, so we gotta be careful. So this is region 1, and it's region 2. Let's pick t equals 1. 1 is less than 2.7. And then here, let's pick t equals e squared. Okay? Because e squared is much bigger than this. All right, so let's test it. We're looking for a sign change from positive to negative in order to conclude that it's a max. So for region 1, we are testing t equals 1. We're plugging it into the first derivative, which is, what is the first derivative again? Let's see, first derivative. Yeah, there goes the first derivative right there, 1 minus ln t over t squared. So we have y prime equals 1 minus ln t over t squared. Okay, so the first derivative evaluated at t equals 1. Let's see what the sign is. That's all I care about here. So we have 1 minus the natural logarithm of 1 over 1 squared. Okay, so in this case, you're going to have 1 minus 0 over 1, which is 1, which is positive. Looking good. So in interval 1, we have a positive slope. Okay, so that means the function is increasing here. In order for this to be a maximum, this has to be negative. The derivative has to be negative, which indicates that the function is decreasing. All right, so interval 2. Interval 2, we have t equals e squared. I picked e squared because it's easy to calculate. You'll see in a minute. Anyway, so we're going to evaluate the first derivative at t equals e squared. Okay? So we're going to have 1 minus the natural logarithm of e squared over e squared. Okay? So this becomes 1 minus the natural logarithm of e squared. These two cancel out, so it's just 1 minus 2 over e squared. Okay? We know that the numerator is going to be negative because 1 minus 2 is negative 1. E squared is also a positive number. So negative over positive is negative. All right, see why I selected that e squared? Because it's easy for me to take the natural logarithm of it. All right, so it's negative. Excellent. That's exactly what we needed for it to be a maximum. So it's negative in this interval, so the function is decreasing after it passes x, t equals e. All right, so guess what? Since we have a sign change of the first derivative from positive to negative, we have a maximum at t equals e. All right, so let's see. Our answer is going to be option letter C. All right, let's move along to the last one, question 20. It says an equation of a tangent line to the graph y equals the inverse sine of x over 2 at the origin is. Now, two things you need to know here, the equation of a line, point slope form, and the derivative of the inverse of the inverse of sine function, okay, which is also the arc sine. So let's write those formulas down real quick. So the point slope form of the equation of the line is y minus y1 equals m x minus x1. So basically all we need is x1, m, and y1. We're at the origin, right? We're at the origin. It says origin here, so what does that mean? At the origin, we know that x1 is 0 and y1 is 0. So we have two things down. Now what we need m, the slope, okay? We need the slope. How do we find the slope of a line if we just have a point? Well, that's the beauty of the derivative, right? It helps us to find the slope with just a point as opposed to algebra and stuff where you need the 2 points to find the slope. All right, so we need m. If I can find m, I'll plug this, x1, y1, and m into this equation, and I'll be good to go. All right, so to find m, we have to differentiate this function, but we need to remember that the derivative of the inverse sine of x over inverse sine of the x derivative of the inverse sine of x is 1 over the square root of 1 minus x squared dx. Okay? Alright, well dx, we don't need the dx over there, so just yeah, 1 over square root of 1 minus x squared. Anyway, so this is the derivative of the inverse sine. Okay, so why do we need this? Why do we need this? Because we need to find the slope of this function, the derivative of this function, and then if we evaluate the derivative at this point, that will tell us what the slope is at that point, okay? So we're gonna look for the derivative, dy dx. Dy dx is going to be inverse sine of x over 2 prime. So we're going to be using the chain rule here because we have a composition of two functions, a linear function and an inverse function. So the outer function, if we differentiate the inverse sine, we're going to have 1 over the square root of, you know there's 1 minus x squared here, but in this case, x squared is x over 2. So we're going to have 1 minus x over 2 squared. Okay, 1 minus x over 2 squared times the derivative of x over 2 using the power rule is simply 1/2. Okay, so there you have it. We're evaluating the slope at x equals 0. So let's not bother simplifying this. Let's just plug in x equals 0. So dy dx at the origin, the slope of the tangent line at the origin where x equals 0 is 1 over the square root of 1 minus 0 over 2 square times 1/2. Okay, that's going to give us, this whole stuff is just 1 over, this is 0, so 1 over 1 times 1/2, which equals 1/2. Okay, so the slope is 1/2. So now we're good to create the equation of the tangent line because we know we have a point and a slope, and that's sufficient for us to write an equation. So we're going to have y minus y1, 0 equals the slope m, 1/2 x minus x1, which is 0. Okay, so we have y equals 1/2 x as the equation of our tangent line to this equation at the origins. Well, let's see. We don't have it. We don't have any function. Everything is in standard form. So let's make this in standard form. So we make this in standard form. The coefficients of each variable have to be integers. So we have a fraction here. So to resolve that, we multiply by 2 both sides, and then we have 2y equals x, and then we need to set it equal to 0 in such a way that the coefficient of x is positive. So we subtract 2y from both sides, we have x minus 2y equals 0. So there goes the equation of the tangent line in standard form. Okay? Alright, so our answer is going to be option A. Alright, so there you have it. Thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. And you can click like if you like this video. Please post a comment to let me know what you think about this presentation. More clips coming from mathclassserve.com. Thanks again and have a wonderful day.